And do the lab. Again, welcome to the second session of the day. Today is lab, actually. We're still on the same day, April 7th, and we're doing the physics 4B. And today we're doing lab. I have a recording of a lab with another section, but I didn't think that it's going to be worth basically sharing the link. The reason why is because there are some unique difficulties that apparently some of you will run into. So we want to do it together, okay? Especially if you're running an operating system like the Mac OS. Anybody in here has a Mac instead of Windows? You can put it in the chat. No one? Everybody is a Windows machine? Good. Then you should not have that problem. If you're running a Mac, please reach out to me because you're going to have problems with running the JRE, Java Runtime environment, okay? So if you have a Mac OS, you need some fixes, you need some links, okay? Since you have the Mac, let me give you this link. Two of them, as a matter of fact. One of them is, I'm going to put them in the chat, and I'm going to also include them probably for anybody who asks them. So let me put the first link first, okay? Because I don't want to put them all in the same thing, and it looks like it's a big link on the chat session, okay? So this is link number 1 for Mac, okay? If you're not a Mac user, this is not going to apply to you. I mean, there is some issues also that you might run into because Microsoft put the same level basically of restrictions, but you are going to, so both of these links are for those who are using a Mac, okay? The first one is how to actually install the Java runtime in there and to enable it and to make sure that it's allowed to run. The second one, your computer will think, am I lagging? Is my voice coming slow or something? Or can you hear me well?
Yeah, we can hear you.
Very good. So the second link for those who are running a Mac, they will run to a different thing because it will say that the file that you have downloaded, the installation is successful and everything, the download says that Mac OS cannot verify that this app is free from malware alert. So there is a workaround that so that you're going to do it. And again, as I mentioned before during the lecture, is because you have two things to do. You have to install the Java runtime on your computer, Java runtime environment. And there is the link for that in the lab instructions on how to go to it. And it's from java.com basically. And then you need that, not just for this lab, but for other labs also down the road. Okay, so you need that. And then, so do not delete it until the course is over. You do not uninstall it, I should say, until the course is over, in which case you can actually uninstall it if you want to. Okay. The second difficulty you're going to run into is that the file itself, when you go to the FET simulation, and the file itself exists actually on the website for the FET, or you can download it actually from the lab instructions. You can do it both of them. But once you download it and you right-click on it and try to open it, it will tell you that for Mac that it cannot really verify this one if it's free of viruses or not. Therefore, you're blocked from using it. So you need to go through the second link to basically do that. So that is basically how this thing is. So let me go into, first of all, let me find it on my screen in here. I'm doing several things in here. No, not that one. Okay, so let me delete this stuff in here. Delete, yes. Come on. Okay. And let me go down in here and find where the lab instructions is, where in physics, the modules. I need you guys to make sure that you have this lab open, okay? It's lab 4. Where is it? Here it is. It's the RC circuit. So if you look at it, there is an Excel spreadsheet that you will need. There is a lab report form that you will need also. I'm going to open the lab reports lab report form. Now, once I have it open, I'm going to move it by itself in here. Let me make sure nothing else is open on this side. Okay, so I have the lab report form. And then you will need the Excel spreadsheet, which I'm going to download also. I'm hoping that you guys are doing the same thing as I'm doing, because we want to look at everything in here. And then it says to download which it tells you to download that file in there. So you need to download it, okay? So let's go through the lab instructions first. Let me go to share now with you guys. Share the lab. Okay, here is the lab. Okay, I'm gonna skip right now through these things because that's the instructions, but I'm gonna come back to them. Let me go through all of these things and come to where the technical things are, because we want to get it. You will need the Java runtime. Here is the link for it, okay? So you need, on the lab instructions themselves, on this page 4, on page 4, there is this link, the second link, not the first one, okay? The first one will take you to the FatLab website. You can do that from there, or you can download the actual file that I have for you guys. It's the same thing, okay? You're going to be taken to the same place. But before you do that, please do not do this first. Do not install, do not try to, install this one first. Because what I have seen happen in the past, people start with this one first. Your computer doesn't recognize this file, okay? Does not recognize this file at all, which has the extension. Okay, what is that? Come on. It should have an extension .jar, basically, okay? So your computer does not recognize it, and you might be tempted to open it with your browser or something, or Excel or something else. And then you will have to go back into the default programs and remove that and make sure that it's open with this JRE after you successfully have installed it on your computer, okay? Is so far everybody with me in here on this first step, which is on page 4. So you go to page 4 and you go to the second link that says Java Runtime Environment and install that software. If your computer says that, are you sure you want to install it? This is an exe, you say, yes, I want to install it. Because as I was saying in the introduction, this is made by a company called Oracle, and Oracle is one of the big companies, okay? So this is actually a safe software to have. And it's actually a useful one, especially if you're gonna be doing, if you're gonna be doing development of any form, this is actually a good one. And it's actually used also for gaming, for applications, and it's used for a lot of things out there. Okay, basically controlling cameras and controlling all kinds of things. It's in terms of popularity, it's right out there. I mean, it's not too far from C++, and it's not too far from Python, basically, those popular programming languages. How is everybody doing in here?
Pretty good.
Okay, so you did this installation then, or you are in the process of doing it. Okay, this is very important. I really wanted to do it as much as possible live. The reason why is because you're going to run into some issues, and I want to make sure you go through this step correctly. Once you do that, then you're going to click on the second link. So let me click on it. And let me stop sharing that screen to show you how that looks like once you click on that. Once you have successfully installed the JRE from your on your computer, then you're going to go to the link above it and then you're going to see something that looks like this. This one cannot, you see here where it says this coffee thing in here, this requires Java, and that's exactly what that is. The programming language in here that is needed for this one, okay? So Java itself in here, if we have access to, let's still, I mean that thing then. Anyway, you will download it either from here or you download it from the lab instruction. It's item number 3 from the downloads in the lab instruction. Either way, it's the same thing. So when you click on it in the bottom, you'll see that, I don't know if you can see it or not, but it's saying the link and then circuit construction -kit -ac _ en.jar. So once you installed once you have installed the JRE successfully, this file will be automatically opened by it, okay? So that's why the steps have to be in this order. Otherwise, we're going to have difficulty with this thing. So they have to, first of all, install the JRE, then open the .jar file, okay? Does everybody understand the process?
Yeah, I understand it. I tried opening it yesterday, and I went out of order. So now when I try opening it, it doesn't open correctly, or it just says to save it and not do anything. Is there a certain way I have to open it now instead, or do I just have to reinstall?
No, don't reinstall. Go into the folder where you have saved it. And right-click on it and go open with. Are you using Windows, Jason?
Yeah, I'm using Windows.
Okay, go to the folder where you have saved it. Right-click, not left-click. You know, the mouse has 2 clicks. Has a normal click and has the right-click, the other one. And it gives you the context, basically, and what you want to do with it. One of the options is open with. Once you go to the open with, and one of the options should be the Java runtime, JRE first. Okay, it should be as an option if you have installed it. And then you can default to it so that next time when we're doing the same lab or another lab similar to it, you can actually default to the new setting so that you don't have to do it. You just click on it and then it's going to open automatically. Okay?
Okay, sounds good.
Were you able to get to it or not?
Currently doing it right now.
Okay.
Professor?
Yes.
So after you download it, you just open the circuit construction kit file
Yes.
with the Java, right?
Yes. Sarah, did you install Java first of all or not?
Yes, I did.
Okay, so now we should be able to get into this point in here.
Yeah, I'm there, but it doesn't show me this screen. It actually just shows it's already on the, after it's downloaded.
Yeah, after it's downloaded, go to where it's downloaded and open it.
Okay.
You could have saved a folder for the lab. Okay?
Okay.
So when I click on it right now, it says save as or open. So I'm going to click on open. If you guys, do you guys see the screen in here, mine in the bottom where it says open or save as?
Yeah, I see it.
So I'm going to say open because I have oops. It says in here, circuit construction.jar was blocked because this type of file can harm your device. So it thinks Microsoft, and this is true also for Mac, that this is not a good file. Despite of the fact that I have Java installed, it's telling me that maybe you don't want to do this because we don't know what this company is. This is the University of Colorado in Boulder, and this is their thing, but they don't want to, they shouldn't. I mean, why should they? They're making this for education, which is free for all. So I'm trusting these people, so I'm gonna say keep, okay? So I'm not saying delete, I'm saying keep, okay? So once I say keep, it's going to basically keep it on my computer. Now I'm safe with it, so it's opening it. Okay, let me stop sharing that screen and show you how it looks like once I open it. Share this one. Now this is how it opens. I'm going to maximize the window. This is how it opens in here.
Yeah, that's what I'm getting.
Okay, very good. So you're in good shape. You're actually in a very good shape. Anybody who got this far is actually in a very good shape. Jason, I'm worried about you. Did you get to it to open or not?
I haven't gotten it to open yet. I was opening with Java, but like when I click on the folder, it takes me to a subfolder with 3 other folders in it. And I was
Oh,
having the
so
same problem.
you're opening it with a zip file, then it's zipped somehow. Okay.
Should I try deleting it and then re-downloading
Hold
it,
on.
or is there something?
Yeah. Okay. If you delete it. Okay, Jason, can you hold on? When everybody is gone, we're going to go through it. Probably you can share your screen, because I really don't want to record your screen in here because I'm recording. And then we will see if we can troubleshoot it, okay? Not that everybody is gone, because they might benefit from it. The only thing I really don't want to do is record your screen, that's all, okay?
No worries,
So
that's
after
not good.
okay, yeah. After the session, after we stop recording, then we can go into individual screens, basically, and so that we fix it. And you guys can hang around as long as we're not recording, we're fine, okay? How about the rest of you, the other people now? I want to know, how are you guys doing? Everybody else. Are you following through? Okay, I see some chat going on, but I can't. Okay, let me see. Okay. Okay, somebody else has it going. Let me check. Somebody else is trying. Okay, can you tell me why it's not working? Okay, somebody else got it open. Very good. Okay, let me reply to the people who did not get it open. Can you tell me what's the issue? Where the problem is? Again, if you're having difficulty with this part, which is critical, because you cannot do your lab unless you do this, okay? You have 2 options. Either find a partner to work with and hopefully work together on this thing, okay? Or hang around and then hopefully we can get it open. And I really want you to get this stuff working for you, because you're going to be doing this for other labs too, okay? Okay, that's because you're using Mac OS, and you really have to go through that basically those steps and those 2 links to get it to open. I think you need to go through the second link, because for Windows it was easy enough for you. I mean, Windows also has the same warning like this one, but Windows, once you say keep, basically trusts that you're making a good decision, so it takes you to it, like it happened with me here. For others, you really have to go through that link. If you're using a Mac and getting this message like one of you is getting right now, you have to go through those links, okay? And again, if somebody is watching us right now and they're not in class, and I know a few people are not right now, and you're into the same situation with the Mac, please let me know. I'll send you the links, share with you the links, and then you are going to fix the issue too for you guys, okay? So hang on, let's get this thing going, and then we will come to these technical things and hammer them down and fix them. Okay, so let me go back into the sharing of the screen. Share. And I want to share with you guys the lab instructions, because they're still the main thing, okay? So let's go back into the lab instructions from the beginning. Okay, this is our lab. We're charging and discharging a capacitor. That's what this whole lab is all about, okay? You're going to go through the theory. This we did in class already. So this is the charging process of the capacitor. The time characteristic of this one is tau equals to RC. So this is basically how we're. Okay, what is this thing? I'm sorry. I need to cancel something in here because it's slowing down my computer, and my browser is actually being. Let me go back in here. It's still loading. Since. Okay, good. Anyway, so this is the charging of the capacitor. That is the time characteristic for it. The voltage across the capacitor, all you have to do is multiply it by Qmax, remember, was equal to CE. And the voltage across the capacitor is just this charge, which is time dependent, divided by C. So the C cancels, and you'll be left with the EMF times 1 minus exponential negative T over tau. This is the circuit we're dealing with. You have a battery, you have a resistor, you have a capacitor, and you have a switch. You turn on the switch, and then this thing starts to charge. And this is the characteristic. This is a signal actually we're going to be using, okay? We're going to have a charging stage where the capacitor go from full charge up to a certain point. If we're doing this in the lab, there is actually a generator for a signal generator code, where you're going to have this square, basically a signal, okay? This signal that changes every time. For this signal, the way, if it is done that way, it's going to have a period of 24 seconds. Every 24 seconds, it's going to repeat. Obviously, this time scale on the picture is very large. RC in here, and the scale is equal to seconds. That's what tau is. That is too big. Usually, that's not a typical number, as you saw so far from the problems we did in the homework and everything. Usually, it's of the order of a few hundred microseconds or even less than that, okay? So this is just to see the picture of what's going on, that's all, okay? So the frequency for where the actual signal is changing is 1 over this period. So how often this is changing is 24 seconds. We're going to change the signal again. We're going to change the polarity of the battery, basically. That's what that is. So at some point, the battery is sending a signal this way. And later in the future, we're going to kill it, actually, according to the signal. We're going to drop the EMF to 0. Kill it completely so that it discharges, and then trigger it again after 24 seconds for 12 seconds to charge again and discharge, charge, discharge, charge, discharge. This is what we do in the lab. Actually, the generator in the lab is slightly different. It's not like that. The actual lab, I'm not talking about the simulation. Simulation is going to be a little bit different. So in the actual lab, we take, let's say, for example, 10-volt battery, and then we flip it back. So the polarity switches to a negative 10 for battery. So not only we're going to discharge it, we're going to charge it in the opposite direction. So the current, so the polarity flips, is going to flow in the opposite. This was, when it's fully charged, it has a positive charge in here and negative charge in here. When you switch the polarity, now the positive charge will start to cancel the negative charge first. The voltage drops to 0, and then the voltage will reverse now, so that the positive charge will be here and the negative charge will be there. This is what we're going to be simulating actually in the lab today. Okay, this is what we're going to try to do. Okay, we're going to find the time characteristic compared to the theory and do everything that we're supposed to do as if we're doing the actual lab on campus. Anyway, if I wait, since the tau characteristic is 2 seconds in here, after 2 seconds is about 67% of the signal. After 2 more, which is 4 seconds, 6 seconds, 4 tau, I am almost 99% of the current in it. 98.17 is already charged, okay? So by 5 and 6 taus, basically at this point it's fully charged. Then we discharge again. 36.7% now discharged. This is 2/3 of the way, 63% basically. This is 36, 1/3 of it after just a single tau is discharged. If I wait again, 4 taus, after that, I'm left with less than 2% basically charging the capacitor. And after basically, 5 taus, I practically don't have any charge in it. But this is a charge cycle. This is discharge, charge, discharge, charge, discharge. That is the typical, that is a typical lab too. But we're not doing that. We're charging, charge, and we're reversing the charge completely in the opposite direction. So not only it's going to discharge, it's going to discharge and charge in the opposite direction, okay? So this is how this lab is supposed to be working. So this is the square signal I was talking about in here. This is the square signal this is the actual signal that we should really be seeing if we're going to do that. In this example, we're going from, 5 volt to -5 volt. So the signal here between 5 volt and -5, 5, -5. So we're going to, what are we looking at? This is the VR. This is the current in the resistor. So when we look at the current in a resistor, it's the whole story really. That is the story of the current. So the current in the resistor is 5 volt divided by R. So it's going to be times R. So it's going to be 5 volt. So the initial current is high. Then there is a discharge charging cycle. We're charging still. Then after that, we're going to reverse the polarity. So the polarity in this one, the current will go in the opposite direction. and is going to move in the opposite direction, and then the signal repeats this way, okay? So this is what we're going to be keeping tab of in this lab too. We're not going to be worried about VC. That is actually hard to look at. VC looks like this. Instead, we're going to look at the capacitor across the, the voltage across the resistor, which looks like this, which is much easier. You don't have 1 minus exponential. You have just the exponential to look for. So that's what we're going to be doing in this lab too. So this is the instruction of what we're going to be doing. So I'm going to go through the instructions. This is the circuit that we're going to build. And this is the stuff that we're going to do. We're going to vary the voltmeter and do the readings and report the data in here and reverse the polarity. So we're going to be doing increments of times between, okay, so let me get the stuff that needs to be done, okay? So let me go stop sharing, and hopefully you guys can read the instructions to see exactly what's going on in there in terms of all of this detail. So let me share with you my file, which is this one, after you open it. So let me share the construction kit. Okay, so this is the file that you're going to, once you open it. The first thing I would do is get rid of this symbolic representations. I want to get really into what looks like a, I'm going to come in here and do schematic, okay? They're trying to make it look as realistic as possible. So I'm going to do a schematic. I would need a voltmeter for sure. I would need a stopwatch, and immediately stop or pause the play in the bottom. Do you guys see where the mouse is? Pause it first, okay? Then start the clock. Right now the clock is ticking, but because the play is stopped, the simulation is stopped, I don't see anything in here. Case in point, I'm going to start it and stop it from here. So this is how you control the clock, from here, not from here, not from the top. You start the clock and that's it. So, but that's how you control the simulation. You control it by letting go of the time run and then stop it. I'm going to reset back everything. Right now, if I start again, so the clock now is reset. So I'm going to reset it back and leave it running. Do not stop it at all for the entire simulation, okay? So what I need in here, I need a battery. And I don't like this electron stuff in here personally, so I'm going to go to Show Advanced. And one of the options is Hide Electrons. Okay, we want to just see circuit, okay, as if we're doing this one. Increase the resistivity a little, and it tells you that in the instructions to increase the resistivity a little. The view here is just basically the size. Are you comfortable? This is for your own convenience, not for anything else. Are you comfortable with the size that you're looking on the screen? Okay, for me, it looks fine, okay? So if I look at the lab instructions again, I need the resistor, I need the battery, and I need the capacitor, and I need the switch, and I need a bunch of wires. So let me put the battery in here. I need the resistor. Here is the resistor. Probably put it in here. I need the wire. No, before the wire, I need the capacitor. And I need a switch. I'm going to put the switch in here, slightly different than what the picture is in there. Okay, I'm going to move things around in here. I need a bunch of wires. So let me pick up this wire, connect this two. And I need another wire, connect these two, align them nicely. I need another wire in here, just to align things around. I need another wire in here. And I need another wire. If you don't like a junction, you can just break it. Right click on it and it says split junction. Okay. And I need another wire. Because I have the entire play paused, so it doesn't matter. Even if I close the switch, nothing is going to happen. So I'm going to leave the switch open. Okay, and finally another wire to close everything together. Now I have my circuit looking more or less on how it needs to be. The values now, I need to show values. Right now the resistor is supposed to be, if I go back and look at the instructions, it's supposed to be 50 ohms. Okay, so we need the 50 ohm resistor. We need an EMF that is equal to 120 volt, and we need the battery to be the maximum possible. That's what allows us to give it to control the time. If we make it too short, we will have very hard time getting any reading whatsoever. So we're going to make the time. We're going to make the EMF. So you right click on it and change capacitors and change it to the maximum values, which is 0.2 farads, which is a huge capacitance, by the way. We're going to change this one by right clicking on it and change the resistance and make sure it's 50 ohms. Okay. You can get it 50 ohms exactly. So we have that. And then we have the voltmeter. If I do change the voltage, you can clearly see that the maximum voltage I can do is 100. So the only way for me to increase is to say more volts. If I do more volts, it's hard to control it by hand because it can go very high. So I need to have 120. So what I do in this case, I click on here and select all, Control A or delete or do whatever you want to do it with the mouse, however you're comfortable with it, and write instead 120 manually. Once you do that, now the voltage is 120. Sometimes this goes on and off. I still have checked the show values, but it's not showing me values. So I'm going to click on it again, okay? Typically, this is, it needs to have some internal resistance. So I'm going to right click on it again and change the internal resistance to some value just to mimic reality in here. This has no need, but this one actually also, if I right click on it, no, it doesn't give me any control on these things. Anyway, so now I'm going to click again on this one, and now there is some internal. This really looks like reality. Now I need the voltmeter. The voltmeter always have to connect because we need to find VR, by the way. So I need to put the voltmeter across the VR. So right now, it's across the VR. Don't worry about this question mark right now because there is no current running through the circuit right now. So it's not knowing exactly how much to read. So I'm going to close the switch. If I close the switch, nothing is going to happen. The reason why nothing is going to happen is because I don't have anything running. Remember, there is no charge in the capacitor at this point. So the voltage in here should be 0. The voltage in here, oh, why did it drop to 600 and that's not good. Should be 120 volts. Yeah, that's good. 120 volts. That's why it's important to see what's going on to make sure nothing has changed on you. So right now, when I turn on the circuit, right, well, let's close the switch first of all to see nothing happens in here. When I close the switch, the resistance in here is 0. When I have it open, it's infinite. That means there is no current. So right now, its switch is closed. It's like I turn on the switch, but there is no time. Basically, time is frozen. That's why I don't see anything happening in here. So what I'm going to do in here, I'm going to play it for a few seconds and stop it. When I do, the voltage will be very high, around 120 volts, as a matter of fact. This voltmeter should read that high. So I'm going to start it and stop, okay? So after 0.42 seconds, the voltage now is 111 points, whatever, that's 67. The reason why is some of the charge now has already built up in there. There is actually a Q over C there. I can check for it. The voltage there, it should be some small value, 4.75, 4.78 actually, 4.8 voltage in here, already built in there. Okay, if I wait that long, okay? So now I have, at that time, I need VR in my table, which is this value from the voltmeter, and I need this time in seconds, T, which is right now 0.42 seconds. And then I'm going to wait until any time between between 10 and 20 seconds. So I'm going to restart it again and wait until the time now has lapsed so that it's more than 10 seconds. Okay, right now it's 5 seconds. As you can clearly see, the voltage is dropping because the current is dropping. Now it's probably good enough to stop it, okay? At 12.03 seconds, the voltage across the resistor now is dropped to 36 volts. If you're curious trying to see what happened in here, this voltage is increasing. The sum of these two voltages should be around 120 volts. So again, I can check this voltage in here. It's 82.6. This voltage in here is 36.2. 36.2 plus 82 point something is going to be around 120 volts, this voltage, okay? I don't care about this voltage again. All I care about is just this voltage. So this is my second point in the table. The third point in here, I'm going to wait for it until it reaches anytime between 20 and 30 seconds, then I'm going to pause it, okay? It doesn't have to be immediately, by the way, anytime in between 20 and 30. So for example, I'm going to stop at around 25. Okay, that's good enough, okay? So at this point, this will be my third point in here. The voltage has dropped to 9.624 volts after this many seconds, 25.71 seconds, okay? So that's my third point in the table. Then I'm going to wait any time between 40 and 50 seconds. Okay, this is good enough. After 32.34 seconds, my reading right now for the voltage is 5.061. The reason why we got 120 volts in here, we get this number this way so that we can have a decent voltage in here to read, so that we have a high precision, so that the error is minimized, okay? In practice, this is not how we do it, okay? In practice, the voltmeter is around 6 volts or 12 volts, depending on the power source. And this capacitor is a lot smaller than this one, and this resistor is sometimes higher than this one, but it's still, you have, in that case, you have actually the whole equipment will give you all of these values and give you the graph and everything else. So you have better data in that sense in there. But in here, we're trying to do it manually. So between 32.34, this is the third point. So we have between 0 and 10, 10 and 20, 20 and 30, and 30 and 40. The last point in here is going to be between 40 and 50. Okay, wait a little later. Don't have to do it immediately, okay? 48, 47 is good. So right now at 47.19, I have this much voltage. So let me stop sharing the screen. And I'm going to go back into the other screen to share with you the other screen for the lab instruction to see what's going on. Where is the lab instruction? Did I close the PDF file? It's not a Word file, it's a PDF file. I think I have closed it. No, it's here. Okay. So this is basically the first thing in here. I have T1 in seconds. So this is the charging times 1, 2, 3, 4, 5 between 0 and 10, 10 and 20, 20 and 30, 30 and 40, 40 and 50. So I have data in here to get all of the voltages and the times in here. I need now to go through the instructions. Let me go back again. After around 30-second time in the stopwatch, and while the animation is in pause mode, right-click on the battery and select reverse, okay? And now do the reading again between 60 and 70, 80 and 90, and so on and so forth. So you never stop the watch. You keep it running, okay? So we're going to reverse the polarity, and we're going to take the voltage. So let me stop sharing in here. Let me share with you the animation. Okay. So let's wait now until it's around 50 seconds, okay? So that's probably good enough. That's very close from what I need to do. We don't need to collect this data. So right now we're gonna right click on this one, and you see the button in here that says reverse. We're gonna reverse it. So now the polarity has flipped. Remember, the polarity at this point is reading 120 volts this way, okay? So this is the positive, this is the negative. What we're doing in here, we're connecting the negative to the positive. So the positive is pushing current against this one, and the negative of the positive of this one, as if you have two batteries, each and every one of them is 120 volts. Right now it's 119 here, and this one is always 120 volts, okay? So it's 119.9996, which is practically 120 volts. We don't care about those voltages, but my point in here is the first reading, once I start this one, there is a huge current being pushed by this capacitor, which has the polarity this way, and this EMF, which has this same polarity in the same direction. So the voltage now will double. So instead of 120, we're gonna get around 240. So I'm gonna start it immediately after 50, anywhere between 50 and 60, and get the reading. So start it, stop it. You see right now, it's telling me it's a negative number. Why it's a negative number? Because the current is flowing in the opposite direction. It's flowing in the opposite direction because the polarity in here has it read this way. Don't flip the polarity, leave it as is, okay? Because you need those numbers. So that's all you're supposed to do now. So now, anytime between 50 and 60, it's a good idea to keep it up as close as possible from 50. The polarity has flipped. And the voltage now is negative 217.346 volts, okay? So we're going to do another reading between 60 and 70. So now it's going, both of them. So we're going to cancel the positive, the negative that was in there, and we're going to build the voltage against it in the opposite direction so that this one will come back to zero again. I mean, this voltage come back to zero again so that the current stops. So again, anytime between 60 and 70 will do the next reading. Now, anytime after this one is good. So 1, 2, 3, 4, good. Okay. So this is my next reading. This is anytime between 60 and 70. So I have the time, I have the voltage. So I'm going to continue with this thing in here. Anytime after 70 and before 80 is good for my reading. All right, now it's probably good, maybe. Okay, so that's good enough, okay? So this is any time between 70 and 80. That's a negative 18.353 volts, and the time is 76.02 seconds. Now, any time between 80 and 90. So now we're starting to be in the good region, okay? That is good. 84.7 seconds, and the voltage dropped to negative 8.74. So barely there is any voltage in here because the current has slowed down dramatically in this case. And this has already flipped, by the way. As a matter of fact, if I change the polarity, check the polarity in here, I will see it in the negative sign because now it has flipped, actually. There is more charges on this side, negative, and there are more charges on this side, positive. So if I'm looking at it this way, that's why I'm getting a negative number now. So there's positive charges that have flipped in this direction now. So let's continue with this thing in here and continue the reading, because the last point, anywhere between 90 and 100, keep it as far as possible, okay? Let's give it to around 97 or 98 will be good enough, okay? So right now we are in a good region, so we can pause it whenever we want to, but we want to get to the high 90s. Okay, this is good enough. Okay. You're not going to give it positive at all. No matter what time you wait, it's never going to go from negative to positive because that's it. This will kill the current at that point. So 98.91, okay, if you don't believe me, just keep it running, okay? Until the cows come home, this number will never go positive. As a matter of fact, will never, I mean, it's going to become zero because of the fact that the precision, because this is an exponential decay. So right now we're at 120 seconds. It's still a value, albeit it's negative. Just to show you the exponential in here. So the minimum we're going to get is zero reading on it, and that's because of its precision, that's all. If we have a galvanometer, it's going to continue reading. It's going to continue give us negative and negative values. So right now we are at 120 seconds, and we still have a negative value. The current will slow down drastically at the end, but it's still there, okay? So now we don't need these numbers, by the way. Oops, what is that? Okay, we don't need any of those numbers, but just to show you the point in here of the exponential decay. So now it's fully charged in the opposite direction. And this is trying to push charges now on it, but this is fully charged. It cannot push anymore. Look at how much current, because this is the voltage across the resistor is R times the current. So R is just 50 ohms. So the current in here, whatever it is the one that is extremely small. 50 times a very tiny number is 0.0002 right now, okay? We're waiting now 180, barely see any changes, okay? That's why we choose this high value so that we can see actually significant change, at least between that time frame. So now we have waited 180 seconds. This device at some point probably will give you zero, and it does at this point. And don't trust it, okay? There is no such a thing. It's because it's precision. We went outside of its precision, okay? If we have a different measuring device in here, it's with a high precision using a micrometer, a microvolt, or something like that, it's going to continue. Okay. So let's assume that we collected all of those data. Let me stop sharing the screen in here. And let me share with you the lab instructions. So these are where the times are. This is between 50 and 60, 60 and 70, 70 and 80, 80 and 90, 90 and 100 seconds. These are the voltages in here that you're going to plug in. R is 50. The capacitance in here is how much? 0.2. And this capacitance is 0.2. Where am I going to get these numbers? That's where the Excel file comes into play. So I'm going to stop sharing that screen. I'm going to share with you the Excel file. Share the Excel file. So you probably need to enable the editing because I just downloaded it. Okay. I'm going to put 50 here because that's how much R is. I'm going to put the times in here. And I'm going to put the voltages in here. I'm going to put the times in here. And the voltages in here. And these numbers will be provided for me. Once they are provided for me by Excel, the chart at this point doesn't make any sense because we don't have any data. The analysis, we don't worry about that. So this is how basically the data is. The reason why I have it this way is because it's supposed to be in microfarads. And microfarads is 10 to the negative 6. Since it's 0.2, so it's 2 times 200,000 times 10 to the negative 6. That's why we have it this way. So the math works, that's all. And the frequency in this case is 0.01. That is how you're supposed to change it. Every 100 seconds, you're supposed to change it because the inverse of of this frequency is 100. So it's every 100 seconds. That's why we're doing it between 0 and 50 when the signal flips, and 50 and 100 is when it's actually in the negative side. And then after that, it's supposed to repeat. So what I did in the simulation waiting for a long time was not the correct frequency. So the frequency is, this is the frequency of the signal itself and how often it's flipping, okay? So you need all of this data. So this is written for you. This is written for you. This is actually should have been 50 in here. And I should have recorded all of these values in here. So tau, the theoretical tau is this 50 times this 0.2, and it should be exactly what? 10? Yeah, 10 seconds. Okay, 50 times 0.2, or 5 times 2, which is 10 seconds. So that's why we were looking at it every 10 seconds to see what's happened, anywhere between 10 seconds, basically every tau. Okay. Does the lab make sense to you guys? This is how you collect your data and how you put it in the Excel file and how you get it back and all of that.
Yeah, it makes sense. For the Excel file, do you just want us to fill out both tables for on Excel and on the PDF?
I need the Excel file is to compare it with the actual data because you want it on the PDF in here at the end so that you have that, okay? So let me share with you the PDF file to continue the discussion. This is question 2. What is question 1? Question 1 is calculate the tau naught. So they give you the based on these numbers, it should be 10 seconds, okay? So we just did it, okay? So that is the tau naught. And then question 2, based on your measurement, compare the constant you calculated with this one. So it's going to give you the error in here. This is going to be the experimental tau, and this is your percentage error. And this is the voltage that it maxes at. Remember, it's supposed to be 120 volts. It's probably going to give you 119 or 118 volts or something like that. And again, the error is compared to that. And those are the question, how is it related to that? And then show that during the charging cycle, the stage, the voltage across the resistance is given by, well, it's just this expression. What is it? The current is already there. The current is equal to, we did this in lecture, epsilon over R times exponential of negative T over RC. That is a lecture. You multiply that by R, and R cancels, so it's going to be epsilon exponential to the negative T over RC. So that's how that question is. where that constant would be just the EMF itself, which is 120 volts for this lamp, okay? Now, question 4 requires some work, okay? Question 4 show that if we know 2 points, T1 and VR at T1, and T2 and VR at T2, tau is given by this expression. So let me stop sharing. Let me stop sharing that screen and share with you this screen. Share this screen. So since this is lecture from chapter 27, I'm going to come in here and make a line and show what this talks about, okay? Where is my pen? Okay, so this is what it says. At T1, we know that VR at T1 is, and this is going to be just the EMF times exponential of minus T1 over tau, okay? Where tau is equal to RC. And at T2, VR of T2 is simply equal to the EMF exponential of minus T2 over tau, okay? Or constant, okay? The constant will turn out to be exactly the EMF. So in this case, if I take VR of T1 divided by VR of T2, the constant cancels, and I will be left with the exponential of negative T1 minus T2 over tau, okay? If I take the natural log of both sides, it's going to give me, first of all, T2 usually is greater than T1. So which means that I really need to write it as exponential of T2 minus T1, because that is positive time. Okay? It doesn't matter what it is. Even if they are not, it's fine, okay? You can write it this way because the minus minus becomes positive. So even if at the time T1 is less than T2, you can still do the math in here. It's still the same thing. This ratio will be less than 1, and that's it. So the log will also be negative. If you take the natural log on both sides, so ln of VR in T1 over VR in T2 is equal to T2 minus T1 over tau, which means I can have an expression for tau based on the data from 2 points in the graph, which is simply equal to ln between VR of T1 over VR of T2. I'm sorry, that's nonsense. It's the other way around. That's a time, for God's sake. It's T2 minus T1 over ln of VR of T1 over VR of T2. As I said, because this voltage is going down during the charging stage, because the current is going down, this voltage is actually less than this voltage. Actually, it's higher in this case. I'm sorry, it's going down. So initial time, so this is T1, and this is T2. Okay, since the ratio of V1, VR of T1, if you wish, and VR of T2, this ratio is positive, and the difference between these times is going to be positive. T2 minus T1 is positive, and VR of T1 is greater than VR of T2, so the natural log is positive. So this is how we're going to find tau. That's another way of doing it. So this is the answer to the question, basically, is to show this expression is true. So let me stop sharing the question, the screen, and let me share with you the lab instructions. So what you're supposed to do now is change the resistor. Keep it 50 ohms first. Make sure you reset everything, okay? You reset everything and probably restart afresh. You don't want to be have any residual charge in the capacitor. You don't want that, okay? Otherwise, it's going to mess up your reading in here. Okay? You might not be discharging stage. You might be charging stage. The expression will be, I mean, you might be not in charging stage. You might be in discharging stage, which is really not what you want, okay? So you would want to go really truly in the charging stage. So you might need to restart afresh or follow the instructions on how to reset it. So the first time, you're going to read the voltage for 50 ohms. Then you're going to do another one, another time, and read the voltage. And record tau now. Tau, for this case, is going to be this time minus this time divided by the natural log of this voltage divided by this voltage, according to this expression. And you find tau 1. Then do another reading for time tau T3 and record the value for the voltage, and you find tau 2 in here. Tau 2 in this case will be this time minus this time divided by the natural log of this voltage over that voltage, and you plug it in here and find the average of the two times. Now we do the same thing in here, but for 20 ohms. You do the same thing for 10 ohms, and you do the same thing for 5 ohms. What we're trying to see in here is how is tau depends on R. Obviously, it's going to be a linear function. It's going to be a line, okay? We're going to draw that function. You have the resistor now is changing. So you're going to draw the last point first because it's 5, then 10, and then 20, and then 50. So 5 somewhere in here, 10 ohms, 20 ohms, and 50. No, this is not properly scaled if I do it this way. So I have to have the scale correct. So the maximum value is 50. So 1, 2, 3, 4, 5. So this is 50 ohms. The next point I need in the graph is 20 ohms. So if this is 50 ohms, 40, 30, this is where 20 ohms is. So this is the one point, and this is another point. Then this is 10 ohms, and this is where the 5 ohms is going to be. So those are my 5 points in here. Then you're going to find the tau that goes for each and every one of them, and you draw the line. You could use Excel too if you want to, and append that as an Excel file. Okay? You can use Excel to graph this dependency. Now you're supposed to compare the slopes. The slope should be C itself, it should be the capacitance, because tau is equal to R times C. And you wrote tau in here and R in here, so the slope must be the capacitance, which is 0.2. So you're going to compare the slope that you get from here versus 0.2 farads. Does this basically confirm the how tau depends on C or not? Again, and R and C basically or not. So you're going to compute the error by comparing this slope to 0.2, because remember this whole experiment was done with 0.2 farads. At some point it tells you to choose 0.2 farads for the capacitance, okay? Here, the maximum value. So once you do that, you're going to do your conclusion. Barring the issue, the technical issues, I think this lab should not be hard. Any questions related to the lab first, not the technical issues? No? If you guys don't have questions related to the technical issues, I mean to the lab, then I'm going to stop the recording and address whatever issues that you have with the technical ones, and you might be asked to share your screen to see if we can troubleshoot it now. If not, please read through how you get this Java runtime issue fixed for your computer so that you can run it. Sounds like it's a good deal? Okay, so I'm gonna stop sharing the screen. Not stop sharing, start recording actually, I'm sorry. And then, where is the stop record? Here. And then we're going to continue, not recorded, okay?